Hi everyone. So far we have done several questions. How to calculate the Kc, and if the Kc is given, how to calculate the composition, and different kinds of problems. Now in this one we're going to look at how to determine equilibrium concentrations if the initial concentrations and the Kc is given. Now let's look at the problem. Fuel engineers use the extent of the change from carbon monoxide and water to carbon dioxide and hydrogen to regulate the proportions of synthetic fuel mixtures. If 0.250 moles of carbon monoxide, 0.250 moles of water gases are placed in a 125 milliliter flask at 900 Kelvin, what is the composition of the equilibrium mixture? And at this temperature Kc is 1.56. So we are given the Kc. We also given the initial number of moles and the volume. So we can find out the molarity of these reactants since we know the number of moles and the volume of the flask. So the molarity is moles over volume, right? So we need to convert 125 milliliters into liters, and then we can develop the ICE table. Now this is going to be our balanced equation, carbon monoxide with water giving you carbon dioxide and hydrogen. Okay, and then let's see if every atom is balanced. 1 carbon, 1, 2 oxygen, 2 oxygen, 2 hydrogen, 2 hydrogen, it's balanced. So the QC would be then carbon dioxide hydrogen concentrations over carbon monoxide and water. So we can calculate the initial reactant concentrations for these two, since the number of moles 0.250 and the volume 125 milliliters convert into liters 0.125. So that give you both of these initial concentrations 2 molar. So this is our ICE table, carbon monoxide plus water giving us carbon dioxide and hydrogen. So our initial concentrations 2, nothing happened, nothing has been made yet, and our change going to be x, negative x because it's 1 to 1, and if x amount of these two are being reacted, you are making x amount of carbon dioxide and hydrogen. At the equilibrium, what is left for the reactants, you started with 2 molarity. Now x has been reacted, so 2 minus x would be what is left for carbon monoxide. 2 minus x going to be for the water, and carbon dioxide and hydrogen will have x amounts. Now these are our equilibrium concentration. So now we can substitute these values to our QC. So carbon dioxide would be x, hydrogen would be x, 2 minus x would be carbon monoxide and water, like this. Okay. Now we were given in our example question, it says the Kc is 156. So QC now is going to be Kc because we are at the equilibrium, and this is going to be our QC expression, the values from the equilibrium, concentrations from the table, and x times x is x squared, 2 minus x times 2 minus x, in parentheses you can put them together like 2 minus x raised to the power 2, not times 2. Okay, it's a typo here, it has to be raised to the power 2, not, it has to be raised to the power 2. It has to be raised to the power 2, same thing, raised to the power 2, right? So if you have the denominator and the numerator raised to the power 2 and you have a number here, so if you want to get rid of the raised to the power 2, simply you can get the square root of the other side, right? Excuse me. Oh, it's water. So 1.56 square root, and from the other side we have x over 2 minus x. So when you do the square root of 1.56 from your calculator, you will get a number 1.25. So basically it's equally possible to get the positive or negative, because negative times negative also positive. So plus or minus 1.25. So we're going to take only the positive root because it has any chemical meaning, so we ignore the negative root. So 1.25 equals x over 2 minus x. Or what you can do is, now you are multiplying 1.25 by this number. 1.25 times 2, 2.50. 1.25 times x, negative 1.25x equals x. So when you solve this part, you can find out x to be 1.11. So what we want is the equilibrium concentrations. So we know then carbon dioxide and hydrogen going to be 1.11, and carbon monoxide and water going to be 2 minus x, 2 minus x, 2 minus 1.11, right? So carbon monoxide and water 2 minus 1.11.89, and carbon dioxide and hydrogen is going to be x amount 1.11. Okay, another easy question. Now you see here in our reactants, initial concentration for both of these reactants 2 and 2. So we were able to solve x easily like this because we were able to get the square root from this side. Okay, so remember that. Now using the quadratic formula to find the unknown. Now, like I mentioned in the previous one, the shortcut we used to simplify the math in the previous problem, a special case. That occurred because we started with equal concentrations of the reactants. Remember 2. But typically we start with different concentrations of reactants. So we got lucky in the previous one because it was 2 minus x, and then we were able to get the square root and solve for x very easily. Now that is not the typical case, so we got lucky in the previous one. Suppose for example we start with 2 molar carbon monoxide and 1 molar water. The same problem like the last time, but now we have 2 different concentrations for the initial concentrations of carbon monoxide and water. So 2 molar carbon monoxide, 1 molar water. Now the reaction table becomes like this. Concentration carbon monoxide, water, carbon dioxide and hydrogen. Initially we have 2 carbon monoxide, 1 water, molarity and nothing here, and the change going to be negative x, plus x, plus x. So at the equilibrium it would be 2 minus x, 1 minus x, x and x. Now we can come up with the QC. So the QC going to be carbon dioxide, hydrogen concentrations over carbon monoxide and water, like this. Okay, QC carbon dioxide, hydrogen over carbon monoxide, water. Now carbon dioxide and hydrogen, they are x amounts. Carbon monoxide 2 minus x, water 1 minus x. Okay, now look at here, because these two are 2 different ones, right? So we have to multiply them. You know how the parenthesis needed to be multiplied. So 2 times 1, 2, and then you also do 2 times x. That would be minus x. Minus x times 1, minus x. Minus 6 times minus x plus x squared. So plus x squared and then minus 3x plus 2. So this is what you get when you multiply what you have inside the parenthesis. Okay. So at equilibrium, using the value of Kc. In the previous one, remember, we have the value, the Kc as 1.56. So we can use the same one as the previous one, 1.56. So the Kc at the equilibrium 1.56 equals this value now. X squared over x squared minus 3x plus 2. Now to solve for x in this case, we rearrange the previous expression into the form of a quadratic equation. Okay, so if you started with 2 different initial concentrations, in order to solve for x, we have to go for a quadratic equation. Now if you get the form for the quadratic equation, here what you're going to do is you're going to multiply 1.56 with this number. So that would give you 1.56 x squared minus 1.56 times 3. That would be 1.56 times 3, 4.68. You also do this calculation in your calculator and see you get the same number, plus 1.56 times 2, 3.12 equals x squared. So basically you are multiplying these two, x squared. So then you take 1.56 x squared minus x squared minus 4.68 x plus 3.12 equals 0. So 1.6 squared minus x squared will make it 0.56 minus 4.68 x plus 3.12 equals 0. Now it is similar to the quadratic equation. So then your 0.56 is going to be like ax squared, like this, ax squared. A going to be then 0.56, and then the b going to be your 4.68, and then this is going to be your c, 3.12 c, 0.56 going to be your a. So now we have this in the form of a quadratic equation. Ax squared plus bx plus c equals 0. So in our case, a going to be 0.56, b 4.68, c 3.12. Okay, and here it is also given a 0.56, b negative 4.68, 312. Then we find with the quadratic formula in the appendix, which is this quadratic formula, right? X equals negative b plus or minus square root of b squared minus 4ac over 2a. So here the plus sign means that we obtain two possible values for x. Okay, so if you plug the numbers, x going to be equals b going to be 4.68, b squared minus 4ac, b negative 4.68 squared minus 4, a going to be 0.56, c 3.12, and you solve this part and get the square root of that, and then you divide it by 2 times a, which is 0.56. So when you calculate this, you will get x either as 7.6 or x could be 0.73. Now x is the amount of reactants that has been reacted, and also at the equilibrium how much you have products, how much you have. So but only one of the values makes sense out of these x values. In this case, addition of the square root term gave the larger value, which would yield negative concentrations at equilibrium. For example, if you start with 2 molar and then if your x amount, the amount reacted is 7.6, that doesn't make sense, right? Negative 5.6. So there is no meaning. Therefore, x needed to be 0.73. Okay, so x is going to be 0.73. So now we found the x, meaning this x we found as 0.73. Okay, now we can calculate the equilibrium concentrations. So then the carbon monoxide going to be 2 minus x, 2 minus 0.73, 1.27. Water also the same amount. Not water is not the same amount because water initial concentration was 1. So 1 minus x, 1 minus 0.73, 0.27. Carbon dioxide and hydrogen going to be 0.73 x amount. Now since we find these as our equilibrium concentrations, we can put these numbers into the Kc expression and see what value we're going to get. 0.73 times 0.73, 1.27 times 0.27. So 1.6. within rounding of 1.56. And it makes sense because our Kc, remember we considered our Kc as 1.56, right? So the x having these values for the equilibrium concentration makes sense because we almost get the same number for Kc after plugging these solved values for x and the equilibrium concentrations. Okay, so sometimes you will have to go for the quadratic equation to find out the x. Okay, now there is a way that we are going to avoid doing doing the calculations with quadratic equation all the time. So we come up with an assumption. We call it as a simplifying assumption. Excuse me. How do we use assumption? These assumptions given. If a reaction has a relatively small k, what does a small k mean? Small k, equilibrium constant, meaning the reaction will not go forward very fast. Okay, and at the same time, if you have a relatively large initial reactant concentration, you started with a high concentration and also you have a smaller k, so then the concentration change x can often be neglected. Remember what we do, we say, let's say you have started with initial concentration 2 and the amount reacted is x, 2 minus x. So the 2 minus x, we neglect the x amount, we decide 2 minus x is going to be equal as 2. For example, let's say you measure your weight with your wristwatch in your hand, and let's say it comes to be 130. Okay, so let's say your weight come to be 130 pounds. Okay, with your wristwatch, and then you remove your wristwatch and you measure the weight again. Do you think there is a difference that you would become 125? No, right? So it will still be 130 pounds. So having the watch is negligible, compared to the body weight that you have without having the wristwatch. So like that. So the x is very small amount. So the amount that x has been reacted is nothing compared to the initial concentration. Okay, so we're going to assume that. Now, if the assumption results in a change, how do you see if the assumption is valid? If the assumption results in a change that is less than 5% of the initial concentration, the error is not significant and the assumption is justified. So one way we can justify the assumption, what we did like this is, if concentration of A, initial concentration of your reactants, when you divide it by the Kc value, if it become greater than 400, meaning you have a higher concentration of initial concentration A, and then you divide it by the lower equilibrium constant that comes to be greater than 400, assumption is justified, and neglecting x introduces an error of less than 5%. If the error less than 5%, perfect, we don't have to worry about it. We can use this assumption. Let's say your initial concentration A over the Kc value become less than 400, then the assumption is not justified. Neglecting x introduces an error of greater than 5%. So at this point, we have to use the quadratic equation to solve for x. Okay. Okay, so let's look at this example and see whether we can use the simplified assumption or not. Phosgene is potent chemical warfare agent that is now outlawed by international agreement. It decomposed by the reaction. This is phosgene decomposed to give you carbon monoxide and chlorine. And it's balanced. So Kc is given to us. Calculate carbon monoxide, chlorine and phosgene concentrations when the following amounts of phosgene decompose and reach equilibrium in 10-liter flask. Okay, Now we're going to see if we can use the assumption or not use the assumption. So these are the given quantities. We know from the balance equation then when X mole of phosgene decomposes X mole of carbon monoxide and X mole chlorine form. We calculate initial concentrations, define X, set up a reaction table, substitute the values into the expression for QC. Since Kc is very small, we can assume that X is negligible, which simplifies the expression. We must check this assumption when we have solved for X. Okay. Let's see. We can also see, remember the initial concentration. So here we have 5 moles and 5 moles in 10 liter flask. So 5 moles in 10 liter flask. So the amount of phosgene concentration is going to be 0.5. Let's check the assumption. So initial concentration 0.5 and you divide it by Kc. Kc is 8.3 into 10 to the negative 4. So you divide this by 8.3 into 10 to the negative 4. If this is going to be greater than 400, the assumption is justified. Less than 400, we have to solve X by using a quadratic equation. So let's see what number we would get. Now, can you also do this calculation with me and see what number you would get? 0.5 over 8.3 negative 4. 602. So the value is 602 equals 602. It's greater than 400, meaning we don't have to use a quadratic equation to solve for X. We can use the assumption. So let's look at that now. Okay, so this is again we have to do our ice table. Initial concentration 0.5, nothing formed, negative X plus X plus X. Now you know all this stuff. 0.5 minus X, X, X. So the QC going to be these two, carbon monoxide, chlorine over phosgene, X squared over 0.5 minus X, right? This is the initial, the equilibrium concentration of COCl2. And then this is going to be equal to Kc because we are looking at this under equilibrium concentration. This is raised to the power negative 4, not 10 minus 4, okay? Now we can use the assumption, right? Because Kc is small. So we figure out that because it was over 400, we can use assumption. What is the assumption now? Because Kc is small, the reaction does not proceed very far to the right. So let's assume that X can be neglected. Meaning, remember, in our Kc expression, we have 0.5 minus X. So we're going to assume that is same as just 0.5. Okay, so that's why Kc 8.3 into 10 to the negative 4 equals X squared over 0.5, right? So then the X squared would be 8.3 into 10 to the negative 4 times 0.5, and then you get the square root of that. That would be 2 into 10 to the negative 2. Okay. So that was easy, right? Because then we didn't have to go for quadratic equation or long math. So solving for the equilibrium concentration. So then carbon monoxide and chlorine is equal to X, which is 2 into 10 to the negative 2. And phosgene was 0.5 minus X. 0.5 minus X amount is 0.002, which is now, no, it's not 0.002, 0.02. 0.480. 0.5 minus X, 0.480. Okay. Now, is the error less than 5%? Now, we already found that the Kc going to be greater than 4. I mean, the ratio 0.5 over 8.3 to 10 to the negative 4 over 602. Once you find out the X, we can also do the change, whether it is going to be less than 5% or more than 5%. Let's see how to find out that. Change, which is x over initial concentration times 100. If it is less than 5, we will see. So our change is 2 into 10 to the negative 2. Initial concentration 0.5, right? So times 100, 4%. So less than 5%. So less than 5% assumption is justified. Okay. Excuse me. Let's look at now, we have another case where we have 0.1 mole initial concentration. Now let's try to see the same way even before we get started, whether we can use the assumption or not. Initial concentration versus Kc. So our initial concentration again 0.1 molar, right? 0.1 moles in 10 liters. So 0.1 over 10 liters will give you the molarity. So 0.1 moles COCl2, the calculation in this case is the same as the calculation in part A. Now we have initial concentration 0.1 over 10 liters. Okay, so 0.1 over 10 liters will give us the molarity 0.01. So if you check our ratio, 0.01 over Kc, which is this number, you divide it by 8.3 into 10 to the negative 4. Can you do this calculation with me and see what number you get? 0.01 over 8.3 negative 4. That's 12, right? Did you get 12 too? So that is 12, meaning it's less than 400. So looks like we cannot use the simplified version. We will have to go the long way to find out the x. Okay. QC, again this is the expression for QC. X squared 0.01 minus x going to be, it's the same way that you set up now. This is going to be 0.01 minus x, and this is equal to Kc. Making the assumption that 0.01 m minus x equals 0.01 and solving for x. Now let's say we assume, even though that we know that we cannot assume, let's go ahead and assume that 0.01 minus x is same as 0.01, and then we try to solve for x. 8.3 into 10 to the negative 4 x squared over 0.01. When you solve for this one, you're going to get the x 2.9 into 10 to the negative 3. Now if you try to find out whether it is going to be more than 5% or less than 5%, so this is the x which is going to be changed, 2.9 into 10 to the negative 3. Initial concentration 0.01 times 100, that is 29%. So the assumption is not justified. Okay, so we have to use the quadratic equation. 8.3 into 10 to the negative 4, this number, x squared over 0.01 minus x. Okay, now you have to multiply these two together and you have to find out the x from the quadratic equation. Now I showed you in a previous, in the same video, in the previous slides, how to use the quadratic equation. First you multiply this number with this and write it in the ABC form. Find out what is A, what is B, and what is C, and using the quadratic equation try to see if you also gonna get the x as 2.5 into 10 to the negative 3. Okay, so x happened to be then from the quadratic equation this number, and then 1 minus x would be for phosgene COCl2, 1 minus this amount 7.5 into 10 to the negative 3 molar. Okay, so we'll stop